Assalamu alaikum wa rahmatullahi wa barakatuh. The lesson for today is differentiability. Differentiability means is to check whether a function has a derivative at a certain point or not. So we will start with this question. Are all functions have a derivative at any point? If the function has a derivative at any point, so we call it differentiable function. In some cases, the function has no derivative at a certain point, but has a derivative at another point. So we call it's not differentiable at that point, but it is differentiable at another point. So first, we will start with this example. If you look at this example here, that we have a function x to the power 3. And if I want to find the derivative for this function, we know, according to the rules of derivative, is just to bring down the x to the power 3 here. So what we get in this case, and subtract by 1 the result. So we get x 1 over 3 here, and we subtract 1 from the power. So we get 1 over 3 multiplied by x to the power negative of 2 over 3. If I simplify this one by, because there is here negative, so I move it down, so I get 1 over this part. Now this is the derivative. We found the derivative, but can I find the derivative at a certain point? If I find the derivative, for example, at 1, yes, I can find. When I replace 1 over 3, and here 1 over 1 to the power 2 over 3, so it has no problem. We can find it by calculator. But can I find f of 0 or f prime of 0? Can I find f prime of 0? So if I replace here, I'll get 1 over 3 multiplied by 1 over 0. That means there's a problem here. That means f prime of 0 does not exist, which means this function is not differentiable at 0. So how can we know? We shouldn't find the derivative, then we discover at the end that the function has a derivative or not. So there are some properties, some ideas that will tell us from the beginning that the function has a derivative or not. So we will start now with the second part, is how to study the differentiability if we have a graph. So we have learned now that not every function is differentiable at any point. There is a condition graphically if the function is continuous and smooth. Continuous, we know it. The function should be continuous, has no gap, no jump, no infinite jump, no asymptote. And smooth may be a new word or new vocabulary. We need to know what's the meaning of smooth. If you look at this graph here, you can see, imagine or pretend you have a car. If your car can move smoothly on this curve, it means the function is differentiable. If I want to understand this, I say if there is, for example, somewhere cut here, of course the car cannot continue, so the graph is not continuous, and by default it's not smooth, or we cannot find its derivative. In some cases it is continuous, but if I have car here moving here, when it reaches here, it is difficult to go down, so the graph is not smooth. So as we can see here, that if the graph is smooth and continuous, we say the function is differentiable. So that means the function is differentiable if it is continuous, which means if it is not continuous or not differentiable. So if there is a hole, if there is a break, if there is vertical asymptote, all these of discontinuity points make the function not differentiable. Also, there is another case if there is a vertical tangent. If the graph has a vertical tangent. If I have a graph like this, and here the vertical tangent like that, so if the function looks like that, so it has a vertical tangent line, and in this case we say it's not differentiable. Also, if there is sharp turn, sometimes we call it cusp or nodes. So these three cases, the function failed to be differentiable. Let us look at these examples to understand when the function is differentiable graphically. First, if it is not continuous, so we say that it is not differentiable. So clearly here we have asymptotes, vertical asymptotes. So this is not differentiable. Why? Because it has a vertical asymptote. If I look at the second one, also not differentiable. Why? Because there is jump discontinuity at A. This is also not continuous, and not differentiable at x equals 0, clearly, because also there is jump discontinuity. And also here it's not differentiable because it is not continuous, because there is an asymptote or infinite asymptote here. So all these four graphs are not continuous at a certain point, which means they are all not differentiable. If you look at this, the second question here, it is continuous. It has no gap, no jump, and no break, but still it is not differentiable. Why? Because the graph is not smooth. Smooth here, if you have a car here, it's difficult. With this corner, it's difficult to turn. So, or we can say if it has a sharp point or sharp turn, or we call it corner or node. So in this case, the function is differentiable everywhere except the corner. So at x equals 2 here, and at x equals 0, the function is not differentiable. So the function is not differentiable at x equals 0 and x equals 2 here for the second graph. So that means the second case, if the graph has a sharp turn or corner, also we call it not differentiable. If you look at these examples also here, all are continuous. But the problem, this is continuous, but it has a sharp turn. And this sharp turn, we call it cusp. Not corner, we call it cusp. And the other one also, it has what? Cusp or sharp turn. Here we have two sharp turns. So these three graphs, all of them are continuous, but unfortunately they are not differentiable. Why they are not differentiable? Because they have sharp points or sharp turns or cusps. So this is not differentiable. The last one, it is also continuous, but unfortunately there is a vertical tangent. So if there is a vertical tangent, the line that touches the graph vertically, it is vertical tangent, so it is also not differentiable. So these are new cases of non-differentiable functions when there is a cusp or vertical tangents. Now we need to make sure that the function to be differentiable must be continuous and smooth. And we said smooth, it means no sharp turns, no corners, and no vertical tangent. So if you look at this example here, this one, clearly there is a corner. So since there is a corner, we say it is not differentiable at x equals 0. And the second one, there is what? A cusp. And by the way, both sharp turns, but one we call it corner because line with line, and curve with curve we call it cusp. So this is also not differentiable at x equals 0. If you look at this example, clearly there is a vertical tangent, so also not differentiable at x equals 0. And this one, there is a jump discontinuity, so also not continuous. Let us take more examples to understand the idea. Here it looks like smooth, but in fact there is a sharp turn here, and here if I call it corner or cusp, both are correct because it is between line and curve. Line with line we call it corner, curve with curve we call it cusp, but here we can call it cusp or corner, or it's better to say sharp turn. Sharp turn. So it is not differentiable because there is sharp turn. Okay, the second graph here, there is discontinuity point. So because of discontinuity point, so it is discontinuous and at the same time it's not differentiable. And the third one also vertical tangent. Let us move to take more examples. Look here, it's one graph and it has different types of non-differentiable. Clearly at A there is discontinuity point, so not differentiable at x equals A. So x equals A is not differentiable, and the reason is the function is not continuous. The second point, x equals B, and x equals B here, there is sharp turner or cusp. And the third one, which is x equals C, there is a vertical tangent. Let us take one more example to understand this case. Here, state with reason the x values at which the function is not differentiable. So first what we do, we look at the discontinuity points. The graph is discontinuous at x equals 4. So the first point, I can say it is x equals what? 4. The reason, discontinuity point. The second, I can say the sharp turns. There's sharp turn here and there's sharp turn here. So at x equals 8 and at x equals 0, both there is what? Sharp turns. And there is something maybe not clear, which is the vertical tangent here at x equals 11. So again, discontinuity point, which makes the function also not differentiable, which is x equals 4. And cusp and corner are available on x equals 0 and x equals 8. Vertical tangent at x equals 11. So this is how to study differentiability if we have a graph or graphical. Now let's move to the second part of this lesson, is to study the differentiability for a function that has no graph. We don't know what its graph. So in this case, we will study the same lesson but without seeing the graph. So this is the second part, differentiability of a function. As we just explained, that a function is said to be differentiable if it has a derivative. If it has a derivative, but it takes time to find the derivative sometimes. So in this case, we need to take the opposite, where the function or when the function is not differentiable. So if it is not continuous, this is the first case, or smooth. But here I don't have a graph, so we will study it in different way. So let us take about the first definition. A function is said to be differentiable if the derivative exists. It means if there is a derivative at a certain point. And as we know from the previous lesson, which is how the meaning of derivative, and we said the derivative is the limit of the secant line, or it is the rate of change or the slope of the tangent line. And we said that we can find the slope of the tangent line by using one of these limits. So that means we can conclude if these limits exist, so I say the function is differentiable. But before that, I need to check the continuity, whether the function is continuous or not. So we can conclude now that the function is differentiable if it is continuous at that point and the derivative exists. When I say the derivative exists, it means the left derivative and the right derivative. And we know both they should also equal, not only exist. And to find the derivative, we can use the definition of the derivative or the definition of the limit. So let us take some examples to understand. Here I want to study this function. I want to check, is it continuous first or not? If it is continuous, we go to study the second condition. It is similar of saying, I want to study the differentiability of this function. I want to make sure the student or a student can go to the university or not. So first he should graduate from grade 11. Then if he graduates from grade 11, he will go to grade 12. Then if he graduates from grade 12, yes, he may go to the university. So grade 11, I will call it continuity. And grade 12 is the left and right derivative. Left and right derivative. So for any question, I need to check continuity and differentiability from left and right. So how can I study the continuity here? I want to check it is continuous or not. It's easy. You need to check the three conditions, 1, 2, 3, if you remember. But it's easy just to replace the 1 that's available twice here in both functions. If I get the same result, so that means the function is continuous. So when I find the limit from the left, we can replace here, because this is the left one, so we get 2. And if I replace it from the right, which is the second one down, so I get also 2. That means the function is, yes, continuous. So okay, that means this function graduated from grade 11. I want to make sure this function will graduate from grade 12 or not. I want to make sure it is differentiable at 1 or not. So that means I need to find. If we look at this example, we need to check the function is differentiable at 1 or not. If I want to check the function is differentiable at 1 or not, as I said, first we checked the continuity and it was continuous, which means we are checking grade 11. Okay, the function graduated from grade 11. Let us now check the differentiability, grade 12. I need to study the derivative from left and from right. The derivative from the left is to take this function. So using the way of finding the slope of tangent using limits, which is f of x minus f of 1 over x minus 1. So if this limit exists, so we say the function has a derivative from the left. How to do that? F of x here, and since from the left we'll take x to the power 3. So x to the power 3 plus 1. Now what about f of 1? F of 1, I just replace 1 here, so I get 1 to the power 3 plus 1, so it will be what? 2. So it will be minus 2. and down as it is. So now if I simplify more, I will get this one. Now this is a new limit. If I replace, I will get 0 over 0. So I don't replace, so I do factoring. So one of the factoring techniques, which is a to the power 3 minus b to the power 3, if we remember, factoring a to the power 3 minus b to the power 3, we should remember that this factoring equals what? A minus b first, then a new bracket, which is a square, opposite sign, this minus will be plus, ab plus always b square. This is how to do the factoring of difference between two cubes. Now, how can I do this? So I will say that this one will be x minus 1. So this is a cubic here. Then multiplied by x square, opposite sign, which is a plus, 1 by x, which is x, and always a plus 1. So this is the factoring of up. Now, the factoring of down, there is no factoring for down, but now we only do canceling these together. So we get a new limit, and when I replace, I get 3. That means the limit from the left, the limit of the derivative from the left exists and equals 3. That's not enough. It's only from the left. I need to check from the right. So after we found that the function has a derivative from the left, we need to check the derivative from the right. So we'll do the same issue. From the right, when x bigger than 1, so we'll take this function. So, and apply the same rule, which is f of x minus f of a over x minus a. And here, f of x is 2x, and f of 1, I replace x by 1, it will be 2. So it will be 2x minus 2 over x minus 1. And if I replace, as I said again, I will get 0 over 0, which is not enough to stop. We need to do factoring or something else. Here, easy to do factoring. Then I can cancel x minus 1 with x minus 1. So I get the limit equals 1. And this will give me an answer that the derivative, yes, exists from the right. And it was also, so the derivative exists, and it was also exists from the left. But unfortunately, the left derivative doesn't equal the right derivative. The left derivative, unfortunately, doesn't equal the right derivative. Both they have derivatives. We have derivative here till this point. Then we have another derivative here, but with line, which means we have two different slopes, two different derivatives. So we say that this graph is not smooth, although it is continuous. As you can see here, that the function has a derivative from the left and has a derivative from the right, but unfortunately the two derivatives are not equal. So as you can see in this graph, that there is a derivative from the left, there is a tangent, there is a slope, and there is another slope from the right, but these two slopes are not equal. So that means we have two different slopes. One is 2, one is 3. Now let us take another example to check, but we need to remember we should check two conditions: the continuous, which is grade 11, and differentiability grade 12, and differentiability left derivative and right. Let us now take one more example, but before we take any example, we need to make sure, if I want to check the differentiability for a function, I need to study two things. First, the continuity, whether it is continuous or not, and also the differentiability or the derivative. But the derivative has two parts. left derivative and right derivative So both we should study, both should exist, and both should equal to each other. So always, if this condition is satisfied, so that's not enough. I need to check the second condition. So both should be satisfied. So to do that, we'll take this example and we'll see how these two examples work with differentiability as we saw before. So let us take this example. First, we need to check it is continuous or not. So the easy way, just replace 1 in this function and replace 1 in that function. So when I replace, I get here for the first one, I get 1 because 1 is equal 1, and from the right I get 2 by 1, which is also 2 minus 1, which is also 1. That means the function, yes, continuous at x equals 1. At x equals 1. So that means we finish checking the first condition, which is the continuity, which means this function or this student graduated from grade 11. Now the student is going to grade 12, and grade 12 you need to check the left derivative and the right derivative. So to do that, we will again apply the same rule, which is the left derivative, the derivative from the left at 1. I need to use the same, which is limit when x goes to 1 or approaches 1 from the left, f of x minus f of a over x minus a. So f of x minus f of 1 over x minus 1. This is the definition of the derivative. So if this derivative exists, we should check the second derivative from the right. So let us now first find this one. So if I find the derivative, when I replace f of x, I get which function? I get x squared. Why? Because from the left, and from the left it's this one, because this is the left of 1. So x squared minus f of 1, which is 1 over x minus 1. Now if I replace, as usual, we will get 0 over 0. So in this case I will do factoring, and we easily remember the factoring difference between two squares, x minus 1, x plus 1. Then we cancel this with this, x minus 1 with x minus 1 as a common factor. Then we get only 2. So which means the derivative exists and equals 2. But that's not enough. We need to check the second derivative from the right. The derivative from the right. So the derivative from the right, I need to check the limit when x goes to 1 from the right. So which is 2x minus 1. So this is 2x minus 1 is the function f of x. Minus f of 1, I need to replace 1. So when I replace 1, 2 by 1, 2 minus 1, 1. So this is f of 1. So still, I need to simplify more. Then I get a common factor. Then I, as we know, cancel the common factor. So I get 2. And here, the right derivative exists and equal 2. So here we found that the derivative from the left is 2 and the right derivative also 2. So which means clearly the graph is smooth, because the left derivative equals the right derivative. The left derivative equals the right derivative. That means the f prime from the right, we got the answer is 2, and the derivative from the left is also 2. So that means the derivative exists, and also we found it is continuous. So that means the function is differentiable at 1. So that's enough, but we need to remember always that to study the differentiability of a function, we need to check two conditions: continuity from left and right, and differentiability, or the left and the right of continuous. We need to study the continuity and the differentiability from left and right. Thank you very much.